Hello everyone. Let's study about Topless effect. It is defined as the apparent change in frequency of light emitted by a source due to its motion either towards or away from the observer. Now this is the same thing as what we saw in case of sound waves. Even in case of sound waves, if there is an apparent motion between the observer and the source, then the frequency what is heard, what is perceived is different than what is being emitted. That apparent change in frequency is called as Doppler's effect. Even here it is the same definition. So in this case, to understand this, let's consider an observer. For example, think the observer is on the Earth's surface, and let's consider a star. Now this star may directly approach the Earth or it may recede from the Earth. So there are two cases where the star may directly approach the Earth or it may recede away from the Earth. In this case, it's a frequency what the star emits is called as nu. Let's call the star as S. It's nu. So the symbol is called as nu, stands for frequency. Then let the frequency what the person perceives or listen be nu dash. In case of sound, the frequency is understood or the change is understood better in terms of wavelength than in frequency. Let's assume that the wavelength what has been emitted is lambda and what is received is called as lambda dash. Now because of the relative motion of the source and the observer, the frequency or the wavelength what is received would be different. So this apparent change is called as Doppler's effect. Now in this course, we study about something called as longitudinal Doppler's effect. That is because in this case, the source and the observer will be in the same line of sight. Now think of a case where instead of this, if the observer is moving in one direction, and think of the source moving perpendicular to the observer, something of this kind. Let the velocity of the source be some v in this direction. So here the angle between the direction of the motion of the source and observer is 90 degrees. Even here also, since there is a relative motion between observer and source, the frequency or the wavelength what the observer gets would be different. Even here there is Doppler's effect, but this is called as transverse Doppler effect. But in syllabus, what is given is only longitudinal Doppler's effect. Now here, we have a formula which is not derived. It's not required to be derived in this course. It's not derived. So the change in frequency, it's called nu dash. This nu dash would be, and this delta nu would be nu dash minus nu. This is called delta nu, which is the change in frequency. That will be nu dash minus nu. And if we divide that by ordinal frequency as by nu here, this term is called as fractional change in frequency. So delta nu by nu is equal to, it is given as v radial by c, where v radial is the radial component of source velocity and c is the speed of light in free space or vacuum. In cases where the source directly comes to its observer or recedes the same line of sight, imagine in this case the speed is some v, or if it recedes, even then the speed is say some v dash, just different speeds given. So in this case v radial is same as v dash v itself. So here v radial means it is the component of the velocity along the line connecting two objects, which is in this case v or v dash. But think of a case where the source, instead of going directly away or coming towards the source directly, think of a case where the source is moving. Think of this as a source. It's moving at an angle to the line of sight. So it's an angle to line of sight like this. So this would be the direct line or line of sight, and it moves away with velocity v. In this case, we can find two components of v. A component which is along the line of sight, which is called as v parallel in general. The component which is normal to this, which is called as v perpendicular. Now, what you want is, it's only this component which is parallel to the line of sight. This is called as v parallel, and this is called as v radial. So in cases where the source directly approaches or recedes, in that case v radial is same as v only. Otherwise, it is the component of the velocity which is along the line of sight. The same thing when the source moves away like this. Even then, we can find its two components called as v parallel and then v perpendicular. Again, this is what is required. This is called as fractional change in frequency. Now here, this delta nu by nu, this can be positive or negative. Recall delta nu is equal to nu dash minus nu. So based on the signs, based on the values of nu dash and nu, this could be positive or negative. There are two cases here. A case one where if we have an observer stationed like this, and then a star, for example, think of a star. This star is moving away from the observer, moves away like this, from this direction. Velocity say v. Let it emit a source or something. Let it emit a light wave of frequency nu and wavelength lambda. Let the frequency and wavelength perceived or received by the observer be called as nu dash and then lambda dash. Now in this case, since the source is moving away from the observer, the wavelength what it emits is something, and the wavelength what the person perceives is something else. So what the person perceives is different. So this person may perceive different wavelength. In this case, since the source is moving away from the observer, here nu dash would be less than nu because frequency will decrease. Think of sound waves. When the train recedes from the observer, the intensity will decrease. So same thing here also. When the source moves away from the observer, nu dash would be less than nu. But you recall the relationship between velocity, speed and wavelength, then c is equal to nu into lambda, or nu is equal to c by lambda. So from here, very obvious that nu goes inversely as lambda. Means if nu dash is less than nu, means that lambda dash would be more than lambda because it goes inversely. So in this case, the wavelength received would be more than the emitted wavelength. So if you look at the order of Vidkayar, in this case violet as the least wavelength and red as the maximum wavelength. So when we go away from violet to red, wavelength will increase. Since in this case we get a higher wavelength, the shift is called as red shift. So if we talk about red shift, it means the source is moving away from the observer. But keep in mind that we do not always receive red color only. So don't think that when the source moves away, what we see is red color. It isn't. Rather, what we see is a higher wavelength. Similarly, when the source approaches the observer, even in this case also, if the frequency emitted is nu and wavelength is lambda, and the frequency and wavelength received was nu dash lambda dash, in this case, since the source is approaching the observer directly, in this case nu dash would be more than nu. That would mean that lambda dash is less than lambda. So here the wavelength received would be less than the emitted wavelength. Means we get a lesser wavelength, and that's called as blue shift. Here The terms blue and red are only used to indicate an higher or lower wavelength, not blue or red color as thought to be. Whenever we have blue shift, it means the source is approaching towards the observer. As given here, we have an example where there is a source which is moving away from the observer at the speed of 1c. Keep in mind that the formula what we learned, delta nu by nu is equal to v radial by c. This formula is true only for small speeds of the source. Because if the source moves at a very high speed, then this formula is not valid, because this is only an approximation from a general formula. That general formula is derived by using Einstein's theory of relativity. So it's only for small speeds. So 1c is a small speed compared with c itself. So here it's minus 1 because nu dash would be less than nu. So this term would be negative. So it's minus 1c here. Now what is emitted is, think of a source emitting 3 spectral lines, 3 different frequencies. Here don't worry as to how they get these things, it's a different aspect. Just understand that some source is emitting certain spectral lines. Here we have picked up 3 spectral lines at different wavelengths. One is 434 nanometer, other one is 486.1 nanometer, and one more is 656.3 nanometer. This is what is emitted wavelength, and because of its motion, since the speed is quite high here, it's 1c, but 1c is not sufficient to use Einstein theory of relativity, but 1c is still a high speed only. So there will be a bigger shift, because here it depends on speed directly. So the speed is greater, we'll have a greater shift. So corresponding to 34.0 nanometer, what we get is 479.8 nanometer, the different wavelength. So this shift here, the difference of these two in terms of frequency, is called as Doppler shift. Again, corresponding to 486.1 nanometer, what we get is 537.4 nanometer. That's a quite big shift. So what we get, what we receive is higher than what has been emitted. This is called as redshift. Similarly, if think that the object is coming towards the source, then what we get will be lesser wavelength. For example, if it's like 434.0 nanometer, then what we may get maybe like, say for example, 420.3 nanometer. Rough example. Again, don't buy these values. These values or numbers are given just to make understand how the things work. So since here we get a higher wavelength, this is called as redshift. And one more diagram is given here to make the idea more clearer. But the idea is same. When the object moves towards the observer, what we get is blue shift, and when it moves away, it is called redshift.